Part one of our series is entitled Milkshakes and the Financial Markets. In this section, we're going to take a look at utility models and their role in finance. We're going to be talking a lot about utility models, so it makes sense that we go through a few definitions. Utility models in economics. In economics, utility refers to the satisfaction, benefit, or pleasure a person derives from consuming goods, services, or making choices. So I love chocolate milkshakes. Vanilla milkshakes are a waste of time. So for me, my utility of one chocolate milkshake is greater than my utility of one vanilla milkshake. So in this case, if I was comparing utilities, I would say that I would consume a chocolate milkshake. I would much rather have the chocolate milkshake than a vanilla one. Now under core concepts, total utility, this is the overall satisfaction from consuming a given quantity of good or service. So I start out at zero utility, and then I have a utility of consuming one milkshake, the total utility of consuming two milkshakes, and so forth and so on. Now, marginal utility is the additional satisfaction from consuming one more unit. So I have total utility of consuming one milkshake and total utility of consuming two milkshakes. So the difference between those two utilities would be my marginal utility, and this would be the additional satisfaction I derive from consuming that second shake. Then expected utility, this assumes rational decision making under risk by comparing expected utilities of outcomes. What we're going to do is we're going to be calculating expected utilities for 4 investments, and then we're going to choose which investment we would actually want to make. So let's build a utility model for my love of chocolate milkshakes. So if we go to E1, we'll define M to be the number of milkshakes. Then E2 is our utility model. This is the utility of M milkshakes. So now we need a utility equation. And for this, we have to get a general idea of how this graph is going to look. So in other words, for consuming chocolate milkshakes, the first milkshake is going to be great. The second milkshake is going to be not as great. And there's going to come a point in time where my utility turns negative because I'm sick as a dog. So what we will want to do is we're going to have a utility model for my love of milkshakes to increase, then plateau, and then decrease as the number of milkshakes increases from 1, 2, 3, and 4. So that's how our graph is going to look like. So just by taking into account that graph, the shape of that graph, we can model my utility using a parabola. And a parabola is A times, in this case, my utility model would be A times M squared. Remember, M is the number of milkshakes, so it'd be A times M squared plus B times M plus C. That's the equation for a parabola, and that fits what a consumer of milkshakes, his utility of those consumption numbers. So what I've done is I've just taken a look at the table. I've plugged some numbers in from our, if you go to E3, this is our utility model, and we have the parameters A, B, and C. The M is the number of milkshakes, so we don't have to worry about that. But A, B, and C we need values for. These are the parameters to my model. So I toyed around with this model, and I came up with the parameters of A equals -60, B equals 110, and we're going to assume that the C is constant as 0. So to the right, this is what the graph looks like for my utility of milkshakes. So what you can see is it increases as the number of milkshakes increases, but then it starts to decrease, eventually going negative. So when it goes negative, basically I'm sick as a dog. So my total utility definitely at that time is 0. And we can see that the graph peaks at around 0.92 milkshakes and then turns negative at 1.83 milkshakes. So after 1.83 chocolate milkshakes, I'm starting to feel pretty sick, and therefore my utility turns negative. So now what we're going to do is we're going to build a utility model for various investment options. So if we look at that table and go to column A, these are our options. We have the risk-free investment option. We have investment A, investment B, and investment C. Column B is the dispersion of results. And you can see how dispersion factors into column C and D. So for a risk-free investment, we have 0% dispersion. So my payoff given that the market is up equals the payoff when the market is down. And we're going to assume that those payoffs are $1 million. Now, in this case, we're going to assume that the investor has this bucket of money. He makes an investment, and then the outcome is immediate. So we don't have to worry about the time value of money here. So for a risk-free investment, if the market goes up, I get $1 million. If the market goes down, my wealth is $1 million. And if the probabilities, are 50-50, then my expected payoff is $1 million. And you can go all the way down from my risk-free investment to investment A, to investment B, to investment C. So investment C, my dispersion is 30%. So if the market goes up, I get 1.3 million. But if the market goes down, I get 700,000. So E1, this is our initial wealth before the investment. So this is what the investor starts out with, and we're going to assume that that's $1 million. Equation E2, that's our investment payoff given that the market goes up. And in E3 is our investment payoff given that the market goes down. So in column C would be E2, which is a market up, the payoff market up. And column D would be equation E3, which would be the payoff given the market goes down. So E4 and E5, these are our probabilities. So we're going to assume that the probability of market going up is 0.5, and the probability of the market going down is also 0.5. So E6, this is our expected payoff. What we do is we take the outcomes and probability weight it, and the expected payoff is in column E in the table above. So expected payoff would be the outcome given that the market goes up, my wealth, if the market goes up, times the probability of the market going up, plus my wealth given that the market goes down, times the probability that the market goes down. This is our expected payoff, and that's in column E in the table above. And note that my expected payoffs are exactly the same as for the risk-free investment, investment A, B, and C. So in this slide, we're going to build a utility model for the risk-neutral investor. And remember that risk-neutral investors don't exist in the real world, and they exist in theory only, but it's a great place to start. E1 would be the utility of wealth. Capital W is my wealth at any given point in time. So E1 would be the utility of that given level of wealth. E2, that's my initial investment. So this is wealth that I start out with. So what we're going to remember that what we're going to assume is we start out with this bucket of cash. We're going to invest it and get an investment payoff that's immediate. So E2, that would be my initial investment, which would be $1 million. Then E3 would be the investment payoff given that the market goes up or if the market goes down. So now we have to build our utility equation. And just like we did for milkshakes, we have to kind of get a glimpse or an idea of what the graph is going to look like. Now for the risk neutral investor, remember that all I care about is my expected payoff. So therefore the graph is going to be linear. So what I want to do is I want to have E4, which is my equation for my utility model, to be a linear equation. So therefore, in E4, I have my utility of any given level of wealth, whether the market goes up or market goes down, is A plus B times the ratio of my ending wealth over my beginning wealth. So in order to create the graph to the right, I had to plug some values in for A and B in our utility equation, and I do that in that table, where I say that my parameter A is 5, my parameter B is 2. Now it's important to note that given this is a linear equation, my first derivative is positive, and this is what we want to see for all utility models, regardless of whether they're linear or not. And basically that says is that every dollar of additional wealth adds to my utility. We never get to the point where we're sated, where oh please don't give me another $1 million of wealth. We'll never get there. Every dollar of wealth adds to utility, so it's ever increasing. Now the second derivative is 0, and this is because the investor is risk neutral, and we'll see where that plays in the next slide. So in the previous slide, we created a utility model for the risk neutral investor. Right now, we want to take that utility model and apply it to 4 investment options, which we see in column A of that table. So we have 4 investment options. We have risk-free option, A option, investment B option, and investment C option. Now our base wealth in column B is the same. We all start out with $1 million. Column C is a dispersion, and we have 0% dispersion for the risk-free investment, 10% for the A, 20% for the B, 30% for the C, and we'll see how that plays in. Now the next block there is my market outcomes. Column D is my payoff or my ending wealth, given that the market goes up. So we see that increases from $1 million all the way up to $1.3 million, depending on dispersion. And also in column E, this is my wealth given that the market goes down. And it starts out at $1 million for my risk-free investment and decreases to $700,000 for my investment C. Also note that the expected payoff is the same. Remember that we assumed that the probability of market going up was 0.5 and the market going down was 0.5. So therefore, the expected value or the expected wealth would be, at the end of this investment would be $1 million, regardless of what the dispersion is. So now what we want to do is we want to calculate utility. So we're going to take column D and column E and run them through our utility model. So if we look at column G and H for my risk-free investment, my utility is 7 regardless. So therefore, my expected utility is 7. So what I'm doing is I'm taking the outcome, my utility for market going up times 0.5, plus my utility for the market going down times 0.5 to get an expectation. And note that as we go from my risk-free investment all the way down to investment C, my utility keeps going up for the up market, but continues to go down for the down market, but the expectation is the same. So the expected utility for my risk-free investment equals the expected utility for my A investment, which equals the expected utility for my B investment, which equals the investment utility for my C investment. It does not change. It's the same all the time. So we can see this in the bar chart at the bottom there. This is my investor expected utility at the end of that investment, regardless of which one he chooses. And we see that the expected utility is 7 for the risk-free, 7 for the A, 7 for the B, and 7 for the C. So my expected utility is the same. So from the risk neutral's investor's perspective, he is indifferent from investing in the risk-free option, A option, B option, C option. He looks at those as identical, so therefore he is indifferent between A, B, C, and the risk-free option. So now we want to apply a utility model for the risk-averse investor. So just as the same as in the previous slide, E1, that's my utility of wealth, where W is my ending wealth, or my wealth at any point in time. E2, that's my initial investment, still $1 million. E3 is my investment payoff. Nothing has changed. So I have a payoff given that the market goes up, and I have a payoff given that the market goes down. And E3 would be my ending wealth, depending on whether the market goes up or down. Now, in the previous slide, our utility equation E4 was linear. And that basically gave us the conclusion that an investor, as long as the expected utilities were all the same, because it's a linear model, then the investor would be indifferent between the risk-free investment A, B, and C. But this is not the case for the risk-averse investor. Remember that for the risk neutral investor, the first derivative of that utility equation was positive. The second was 0. But in this case, what we want to do is we want to make that second derivative negative. And basically what that says is that, yes, every dollar of wealth adds to my utility, but because the second derivative is negative, it adds to my utility, but in a ever decreasing manner. So what we want to do is we want to take the equation E4 from the previous slide, and we want to make it nonlinear. So what we do is we take the natural log of that ratio of my ending wealth over my beginning wealth. So therefore, my equation E4 becomes um, my utility of my ending wealth, or my wealth at the end of year one, is A plus B times the natural log of my ending wealth over my beginning wealth. So again, I'm going to use the same equation parameters, A and B, but note that the first derivative is positive, which means that every dollar of wealth adds to my utility, but the second derivative is negative, which means that yes, every additional dollar adds to my well-being, my utility, but in an ever decreasing manner. So therefore we get the chart on the right-hand side, which you can see is nonlinear. So at the beginning, as we go from $200,000 in wealth to 1.8 million, yes, the utility of each 100,000, my marginal utility of each 100,000 is positive. That marginal utility gets less and less and less as my wealth increases. So what we're doing here is given the table. That table is exactly the same as the table from the previous slide, but the utility numbers are different. In this case, our expected utility, if we go to that very last column, starts at 5 for the risk-free investment and decreases from 5 to 4.9 something, and then decreases again for option B, and then decreases again for option C. So in this case, from the risk-averse investors' perspective, my expected utility decreases as my dispersion increases. So therefore, if we can take a look at the bar chart there, my investor expected utility is 5 for my risk-free investment, but it decreases to 4.9899 for my investment A, and then decreases again to 4.9592 for my investment B, and then really decreases for my investment C, where my utility is 4.9057. So in this case, if the investor was forced to choose, if the investor was basically saying that if if you want to invest in option A or my risk-free or whatever my investment option is, it's going to cost you $1 million. So therefore, this investor would opt for my risk-free investment over all the others because my expected utility from my risk-free investment is greater than the utility I derive from investment A, investment B, and investment C. And here's where we come into actually quantifying risk. Remember that in the introduction, we had a graph of risk and return. And under the risk section, we couldn't put the risk of losing my shirt, the risk of running out of money in retirement. We actually had to put a number in there. And in this case, if you look at the expected utilities, they decrease as the dispersion increases. So therefore, we're going to use that dispersion as our measure of risk. So for the risk-free investment, my dispersion would be 0. For A, it'd be 10%, B, it would be 20%, so C is 30%. So these would be my risk factors. So come join our community at Whaddadunce.com. It should be fun.